When it's the same. One of the challenging and showing us to use NGSolve together with PETSc and PETSc with NGSolve. Okay. As I said, so Umberto is the one who connecting all these Firetrack, Phoenix, NGSolve. Umberto is the one who connecting the communities between Firetrack, Phoenix, NGSolve, PETSc, going to all the user meetings of the packages, maybe more, and showing how to connect one with each other.
Okay. Thank you, Joachim, for the introduction. So this is joint work with Patrick and Stefano. But the first thing that I want to show you is that there are 3 different interfaces to NGSolve. Sorry, to PETSc and NGSolve. So which one do you need to pick? You need to pick the one with PETSc uppercase, right? Or if you want to use one of the other, there is one that gets shipped with NGSolve, which is NGS2-PETSc. And then there is the ones written in C++, which is NGS/PETSc. So this is the one, which is Lucas. Yes, where is Lucas? I don't see Lucas anymore. So I will be presenting this one. Advantages of one, advantages of the other. There are a couple of things that you can do here that you might not be able to do in the old interface, but the old interface runs very, very smoothly. So that might be enough for you. So, OK, what am I going to show? PETSc-VEC and PETSc-MAT, so this is the documentation. I'm going to go through some of the example in the documentation, so you have a certain feeling for what do we do. Yeah, so this will show you how to code pinvt by Ignatzev using PETSc basic constructor. Not going to show you that. I'm going to start with solving the Poisson problem with different preconditioning strategy. So this is the variational problem I'm considering. I am, can you see, should I zoom in? No, I shouldn't have zoomed in, okay. So, import MPI word, construct everything in parallel, assemble my bilinear form, assemble my linear form. So far, it's standard NGSolve. Now, what I'm going to show you is that you can query NGS-PETSc to get a Krylov solver. This is going to wrap a Krylov KSP. So you get all the Krylov, so you get a lot of Krylov solver. The first thing we're going to do, we're going to solve with mumps. So this shows you, for example, that you don't need to use mumps wrapper from NGSolve. You can, or SuperLU, or all the different wrapper that are there in PETSc. So mumps, SuperLU, Trillinos, you get them there. So what we're going to do here, we're going to pass the bilinear form, we're going to pass the Freedovs, and we are going to say that the KSP type is going to be a pre-only, so this is a direct solver. We're going to solve with an LU, and we're querying for mumps. So if you are running in parallel, your LU is going to be parallelized. And this is the exact solution. We are grabbing the solution from the solver, putting it into the grid function, and then this is because PETSc likes to do things in this way. It likes you not to return stuff, but to fill stuff. If you're used to C, I guess this is the way things are done. And compute the error draw. So this is an RST notebook, so all the code are available, but it's not a Jupyter, so you don't see the output. And this is because my kernel always fails. And then I prefer to run with MPI exec my RST file. Now, you can use CG, for example. You can use, just to mention a few, you have CG, you have GMRES, you have B-stabilized CG, you have enhanced B-stabilized CG. Sometimes it's also called B-stabilized CGL, where L is the number of steps of your enhancement. You have MinRes, you have a lot of linear solver that you can play with. Here I'm using I'm doing an incomplete LU factorization using it as a preconditioner, and I'm saying that I want to compute the incomplete LU using PETSc rather than using an external package like mumps. And the syntax is the same. So just customizing the dictionary, you get a lot of feature that you might want to try out. So a PETSc LU preconditioner, for example, takes 166 iteration to solve the Poisson problem, which is horrible. So let's try to do things better. How are we going to do? We're going to use PETSc GAMP. So this is the algebraic multigrid preconditioner inside of PETSc. And we are going to run CG. We're going to query for GAMP. And what we get is 35 iterations. So in 35 iterations, we have converged. Still, not great. And I've turned this. So this is an option that will allow you to see how the residual evolve in your PDE when you run it. I will show you it if we have time running one of this code. OK, still not good enough. So what I'm going to use, I'm going to use BDDC. Now, this is a BDDC that you do not have in NGSolve, because in NGSolve you have element-wise BDDC. This is patches BDDC. So depending upon the number of domain that you have, you use the subdivision of the mesh in patches, and then you run BDDC on each patch. So we run with 2 patches to start with, and we converge in 10 iteration. We run with n patches, so increasing the number of patches, of course, the number of iteration grows. Because this is essentially doing direct LU on 2 patch, right? Then I'm doing direct LU so I'm dividing the problem, making it smaller, doing LU in parallel with mumps, and then running this. Now, where is Vink? OK, there you are. So this was the last user meeting, and then somebody written in the forum, your code sucks, essentially. And he was right. My code sucked in the sense that if you run this, PETSc need to have a PETSc matrix to assemble it. You're not going to be able to construct a preconditioner if the matrix is not in PETSc. So we get an NGSolve matrix, we construct a PETSc matrix, we assemble the preconditioner. But sometimes this is not what you want to do, because NGSolve has great preconditioner already in there. Another title for this call could have been coding stuff that Joachim has already coded. How do we do this? We can use any type of Krylov solver with an NG matrix, just squaring for the action of the NG matrix, and keeping my PETSc matrix in a matrix array format. And this is this flag here, so NGSolve matrix type Python. And this is going to run all your solver. And so I'm constructing a solver. I'm grabbing an element-wise BDDC preconditioner. And then I'm assembling the matrix. Notice this now has happened after, because this is the way you need to order stuff if you're using NGSolve preconditioner, not if you're using PETSc preconditioner. And then here, for example, I could run destabilize CG, and this would run destabilize CG with the element-wise preconditioner by NGSolve without having to actually assemble anything. So this is going to be faster. So thank you. Now, PETSc. Yeah?
In parallel also?
Yeah, all of this works in parallel.
P-version BDDC needs a low-order solver. So we could use a PETSc AMG for our cross-grid solver for the BDDC.
Yes, we could do that. This is something we need to try, yes. Actually, I'm going to show you composing. Yes, if I have time, I'm going to show you how you compose PETSc solver inside of NGSolve solver, and you create coupled preconditioner. So you can use PETSc preconditioner inside of NGSolve preconditioner. Solving, linear elasticity. Anybody of you has ever solved linear elasticity? Perfect. Linear elasticity is great, right? If you solve it with a direct solver, it's amazing. If you want to solve it with an algebraic multigrid, you're gonna end up seeing something of this form. 19 iterations. So P1 elements. So I'm far away from the incompressible regime, or I'm using P1 ISO P2. But let's assume for a moment that I'm actually away from the incompressible regime. I get 19 iteration of my geometric algebraic multigrid. Now, one thing that we can do is we can give, this is Hypre. It's another, no, this is actually GAMG. Sorry, so perfect. I've written Hypre here. It's actually GAMG. So bad advertisement for PETSc, sorry. We can give more information to our algebraic multigrid solver, which is what are the rigid body motions. So what is actually the null space of the same bilinear form without the Dirichlet boundary condition. This is going to allow it to construct a kernel capturing prolongation, so we're going to get a better preconditioner. How do we do this? We grab a null space object from NGS-PETSc, we assemble the rigid body motion, we pass them to the null space constructor. This is going to orthogonalize your basis function, and we set the flag near, because this is a near null space. This is the name of this information we want to pass to an algebraic solver. Dictionary. But then when we are running our solver, we're also passing the null space. By the way, you can also pass any null space that you want. You can also, if you remove this, you're passing the true null space. So if you want to solve a PDE with a null space, you can pass it this way. But now we get a significant speed up. So we are converging in 6 iterations rather than in 19. And this was in the DolphinX documentation, and I know that Joachim, you wanted to have it also here, so we have it. Now, we need to present something from Pavia, or else we wouldn't be happy. Buffy-Lovandin augmentation. So this is a P2, P0 element, also known as the Bernardi-Ragel. There was a paper, I think in '96, I wasn't yet born, from Buffy and Lovadina, where they add an augmented Lagrangian preconditioner. Now, let me try to explain what we are doing here. So we are solving Stokes or incompressible elasticity, as you prefer. And the first thing that I'm assembling the linear system, and the first thing that I want to show is something that it has already been shown by Philip, which is a sure complement preconditioner. So I'm going to take the exact inverse of my matrix A, and I'm preconditioning on the 2-2 block with a sure complement. Now, if the bilinear form has 0, the original system has 0 in the D block, so in the 2-2 block, it has been proven by Sylvester and I don't remember, and he's in Oxford, I should remember. Andy, thank you. By Sylvester and Andy Watton that this is going to converge in 3 iteration. So what I'm going to show, don't do this. Don't run this code. This is horrible. It's just to show you that this is how things work. So I'm grabbing a NumP matrix. I'm assembling the inverse of the sure complement because I just wanted to show that if you invert directly the sure complement, you actually converge in 3 iteration. Very directly the sure complement, we converge in 3 iteration. This is don't run. This is not a good idea. It's just to show that theoretically this works. Perfect. Now that this works, we know that we need to find a substitute for the sure complement. Philip, what do? Mass matrix, right? We do the mass matrix, as you pointed out. So if you have an inf substabilization, you can precondition with your mass matrix. Perfect. So this is what we're going to do here. We're going to assemble a mass matrix which is scaled by the density of the fluid. This is going to be important. And then we are going to invert the mass matrix directly using LU. Now, who's going to tell me why this is a stupid idea? I'm doing P2, P0. What is the mass matrix of a P0? So I can use Jacobi. So this code needs to change. I can use Jacobi here. So I'm going to run with Jacobi. This is what actually we run in another example. We are assembling the mass matrix. So this is my mass matrix for the preconditioner. Sorry, the block matrix for the preconditioner. I have the direct inverse of my stiffness matrix. I'm going to show you in a moment what we can do to invert this object. The mass matrix. And I run the solver. How many iterations are we going to converge? 66 iterations. Is this good? Is this bad? I'm doing the unit square. I'm doing lead-driven cavity on the unit square, but this is just to show a couple of things. If you add the whole, this becomes a completely different problem. But let's start seeing what happens here. So you have the mass matrix, and we are doing the LU. This is not good. We want to do something better. We are going to do a vertex patch smoothing with P multigrid. So we're going to do P multigrid, and we're going to add a vertex patch to make this work. The thing that I want to stress here is that NGSolve, at least the last time I checked, but Joachim, you always add new feature, doesn't support smoothing in parallel. Yeah?
But do you use a direct solver for A?
I was using a direct solver for A, now I'm using P multigrid for I'm going to show you what happens if we use P multigrid for A with vertex patch. Before I was using P. Before I was using a direct solver. Now I'm going to try to see what happens if we invert using P multigrid with a vertex patch smoothing. Exactly. Yeah. I'm not expecting this to improve. I'm going to show you how to improve this in a moment. Okay, so now what I'm doing here, I'm grabbing my vertex my DOF's information to construct the blocks. And NGSolve still doesn't support block smoothing in parallel.
Lucas version.
Yeah.
Into.
Okay.
Yeah, but it's not in the master branch.
Okay, perfect. I didn't know this. Sorry, Lucas. So what we are doing here, we are grabbing a PETSc preconditioner. So this is a preconditioner that we grab directly from PETSc, assembled on the matrix A. We are passing the vertex degrees of freedom, and we are saying that we want to invert this object with hypre. And later on, I'm using standard PETSc smoother. I will show you later on how we can do parallel smoothing also in NGSolve doing block inversion of the LU. Sorry, block inversion with LU. But what we get if we run this, so mass matrix plus 2 additive preconditioner, as you pointed out, we do not converge and we get 100 iteration. So we have a horrible, horrible situation. Multigrid doesn't work. Our mass matrix is not a good preconditioner. How are we going to solve this? Well, the answer comes from an Italian, of course. We do an augmented, this is the work by Patrick, many people. So Patrick, Benzi, this is the Italian I was mentioning, but originally it's from Glovinsky and Fortin. So the idea is to augment your Lagrangian with this term here, which is 0 in the limit, in particular if you're doing a conforming exactly divergence-free discretization, like a Scott-Vogelius element. But in the way that Benzi looked at this, this is still going to be 0 because here you're putting the divergence matrix of the P1 element if you're doing Hood-Taylor. But at each iteration of your Calero space, since you haven't reached convergence, this is not 0, and this is going to help you out. So we consider this formulation, which is consistent, because the divergence of the space is 0. And we are going to construct as AG is now my augmented block. I'm inverting it using direct inversion. We see what happened. But we are using as mass matrix the mass matrix scaled by 1 over nu, so the viscosity and the augmentation. What do we get? We converged in 2 iterations. Why? Because the augmented Lagrangian block improved my spectral equivalence. So the stronger I put my penalization in gamma, the better is the equivalence. And this was already in your PhD thesis, right? Okay. And then what we are going to do, we're going to see how can we invert the velocity block quickly. This is not how you do it, by the way, but let's have fun and use some stuff. So we do a 2-level additive Schwarz preconditioner with pre-multigrid and vertex patch. This still doesn't work. We got 100 iterations. We are doing worse than before. So what we are going to do, we are going to look at this in matrix format. This is a low-rank perturbation of this object. So what we are going to do is we are going to use Sherman-Morrison-Woodbury. So we rewrite this object as this object. Then we invert this object directly. We have no gain, but let's see what happened. So we converge in 84 iteration. In particular, if you can use the mass matrix the gain is to use the mass matrix instead of this block over here. And then you converge in 84 iteration. So we have reached in 84 iteration convergence, and we are not doing any direct solve. This is not good. Let me show you how you're supposed to do this. And I'm going to do it for the augmented, for the OSIN problem. So I'm adding a level of difficulty. I'm adding this term right here. Now, what I'm going to do is I'm going to set my gamma. I have my divergent, I have my augmentation block over here. I am going to create my mesh. And I'm going to create my mass matrix, which is augmented with my gamma. I'm going to start inverting on the coarse space, so my problem, okay, with a direct solver. But this is on the coarse space. Then I do I do 1 level of refinement, because I just wanted to show you how this works. You can do it with as many levels of refinement as you want. And then I'm going to solve with using the direct inversion of. Sorry, no. I'm defining the block matrix of my problem, and then I am defining a smoother. So this is a smoother constructed in PETSc. So a PETSc smoother is an SMM preconditioner. So this is a smoother that is going to run in parallel for the matrix A. And if you look at the flag, so let me move this. So ASM is just saying that you are doing a block type of preconditioner, and how are you inverting each block associated? So the blocks are associated to a vertex patch, right? What is a vertex patch? You take the degrees of freedom associated to a vertex, and you remove the one on the outer edge in the patch. And this works because the patch remains, the problem on the patch remains divergence free, and in particular, the problem on the patch respects the Fick complex. So this is how you prove this works, but not really important. I'm inverting this with a LU. I'm using a 2-level additive. I'm using a 2-level additive Schwarz precon. Where was I? Here. I'm using a 2-level additive Schwarz where I'm using H multigrid, and I am using my mass matrix for the augmentation. Now, why do I have to do this vertex patch? This is Joachim PhD thesis, and the idea is that you want a prolongation and a relaxation that are kernel capturing. Your prolongation is not going to be kernel capturing unless you have this type of smoothing. So we code this in, we run the solver, and let's see the performance. So if I start, I'm not scaling here with H, I'm scaling with the Reynolds number, because the difficulty becomes the Reynolds number here, because it's the OSIN problem and not Stokes, right? Stokes, you can lower the viscosity. This really doesn't matter. You're scaling your solution. Here, it does. So a Reynolds number, 10 to the 2, it takes me 2 iterations to converge with this precondition. And I'm not doing any direct solve except from the coarse level. So this is very efficient. 10 to the 3, I'm doing, it converges in 3 iteration. 10 to the 4 Reynolds number, it converges in 5 iteration. 10 to the 5, it converges in 6, 7 iterations, something like that.
What is the brackets?
The tolerance that I imposed on the linear system.
What was the time you need for solve?
This runs in 10 minutes, something like that.
No, but I mean, so.
No, this is the tolerance. This is the residual that I get at the end. I impose the residual, right? So I'm stopping my meter when I get to 10 to the minus 5 because it's enough. I don't need to go below because the approximation error wouldn't be captured. One thing that I think is important here, where is it? Is this. So there are two GMRES solver implemented in NGSolve. One is the Python one is the C++ one. I tried to run this code with the C++ one, nothing worked because the C++ GMRES doesn't play well with block matrix. You need to use the Python one, as I know today. And so instead, I ended up recoding Krylov solver for block matrix. So now you can do matrix nest, and you can use any type of PETSc Krylov solver with block matrices. So you can also do B-stabilized CG and so on, even with block matrix. And this was thanks to the fact that we coded the action of the matrix like you do in GMRES in Python rather than in C++.
The GMRES solver is 15 years old or older.
Yeah.
If you could use now the same style of coding in C++, what we use in Python.
Oh, okay.
It's not a great vector, but just creating a vector and it's a valid vector.
Okay, but will it work in parallel?
No one will ever maintain the
Okay. Okay, but this works. This works for us. So we have now also, so you can also play with block matrix and PETSc solvers. I have another 10 minutes. Okay. I went too fast. Gosh. Okay. No. So let's do let's see how we solve a nonlinear system. So I'm gonna go slower. We are solving we're on a hyperelastic beam. So we are gonna have our two element parameter. This is the energy we want to minimize. C is our right Cauchy stress tensor. You've probably seen this morning. I missed it, but you for sure have seen some similar problem. I'm assembling again I'm generating my mesh in parallel. Well, I'm generating my mesh. I'm distributing it, so I know that the problem is parallel. Assembling the quantity of interest, assembling the energy. And then I'm doing a continuation. So this is my load, and then I'm going to extend on my load. And what I'm doing is that I'm twisting the beam slowly. And how do we solve this? We query NGS-PETSc. Sorry?
Is your matrix asymmetric?
No, it's not. Okay, I need to correct this. The matrix is not symmetric.
It's the same as the morning.
Because we grabbed it all from the same tutorial, I guess. Okay, perfect. So it's not my fault. Anyway.
I put it in on purpose to see who is copying.
I was not the one. So we grab a nonlinear solver. We grab a nonlinear solver. So from NGS-PETSc, we grab a nonlinear solver. We say, I want a nonlinear solver, and now we set the flags. What are the flags? I'm using Newton with least square. Now, I think here the point is that Newton with least square is already coded in NGSolve. So, bad example, we could have used Newton with thrust region, for example, that is something that you don't have in NGSolve. We could have used BFGS. We could have used, there is a plethora of solvers that are available in PETSc that I suggest you check out. We are setting the maximum number of nonlinear iteration. We are saying that we want to see the residual of the nonlinear iteration. And you can play with any of the preconditioner that I showed you before. Now I'm using LU because it was easier, but so direct inversion with LU. But if you here say, for example, you want to solve the each iteration with CG, you put here CG. You want to use hyperrep as a preconditioner, you put hyper flag here. You're running your nonlinear solver with where each linear iteration is solved with hyperrep. Solved with CG and precondition with hyper. Here I'm putting some flags. So I'm saying I want dumping equal to 1. I want my linear searcher to be of the basic type. There are, I think, 4 different types of linear searcher coded in PETSc Newton linear search. So you can choose the one that you prefer. And I'm saying how many iteration of the line search you might want to do. And let's see the result. Dumping 1, NGSolve diverged. dumping 0.5, NGSolve diverged. Dumping 0.3, NGSolve converged. So you get the result that you want. If you do some sort of fine-tuning, PETSc works more as a black box. It doesn't matter what, you don't need to choose that many parameters. Well, in all fairness, you do, but they're standard, so you just copy and paste, and you converge in 10 iteration, 10 nonlinear iteration. And this is the result. This is the only video I have, so enjoy. Okay, so this is twisting. We can continue as many times as you want, really, because the point is that if you want to twist another time, you simply do another continuation, and the number of nonlinear iteration is going to grow. What did I do wrong?
I think the program gets unstable when you're twisting too much.
Not that I have seen, at least, but there might be something that I only tried 2 iterations, at least, but this might get more and more unstable. And you might need to get a lower continuation.
You're going to find a mesh.
Yeah, I should have done a finer mesh. This is fair. Eigenvalue problem. So the original reason why I got into NGSolve and I got into PETSc was not to use in particular NGSolve, nor to use in particular PETSc. So I was there for the wrong reason. And it was to solve an eigenvalue problem with SLEPC. So we can solve eigenvalue problem in a quite an easy manner. So here I'm going to show solving the Laplace eigenvalue problem in primal and mixed formulation. Where we are going to generate the mesh in parallel, we're going to assemble the problem as usual, and then we're going to pass a pencil rather than so the standard eigenvalue problem has this on this other side. We want everything to be written as equation because we support also a polynomial eigenvalue problem. You pass the element of the stencil, so what goes in front of the order 1 matrix, what goes in front of, so lambda equal to 1, lambda equal to 0. If you put something here, it's going to be lambda squared, and so on. And here we are going to solve with locally optimal block PCG. And we get the first 10 eigenvalue. And I will show you the code running if we have time, but you get the first 10 eigenvalue. You can also solve in mixed form. The problem in mixed form, this is a bit trickier, right? Because you have now a mass matrix that has got a very large kernel. So as long as you have the in-sup condition, you know that the 2 kernels do not overlap. So you're happy. And you can invert the stiffness matrix. So this is what we're going to do here. You cannot invert the mass matrix because it has got this large kernel. You can do other things, but let's keep it simple. So we are going to do a shift and invert, which means that I'm going to shift. The problem that I'm going to solve is going to be a minus sigma b to the power of -1 times b. And I'm going to solve the inversion using LU and in parallel using MUMPS. And here I'm getting the eigenvalue and the eigenmodes out of it. So I think I've showed you everything, and I managed to be almost on time. So nothing, just one last thing, which is during this project we also started adding feature to Firedrake. So now Firedrake has no support for any NetGen mesh and any also high order NetGen mesh. So this was nice. We managed to add feature on both sides. So that's it.
Thank you. Like very much has a language here interact. So you have this operator, and at some point you don't know is it NGSolve, is it PETSc, operators.
Yeah, so we tried to keep it simple. Everything that is PETSc related start with PETSc, except from the ISM preconditioner. So it's going to become after today PETSc ISM preconditioner.
Are there some immediate questions?
Do you provide doc strings? Or do we know all the? Ah, yeah, okay.
What do you want?
Like all the flags that can be set. Okay, good.
Manual page. And you go nuts. It's gonna take you. It's a 100-page manual.
Yeah, that's
so
why I'm asking.
so you enjoy. So just to give you an idea of the linear solver and the preconditioner that you can use, let's go here. This is the list of all the different linear solver that they have implemented.
This is not the work you have to do for the interface.
Yeah, sure.
This is coming from CPC.
Yes, exactly.
they are not getting crazy with.
No, I've not done this. No, I'm not crazy. No, don't get me wrong. Where is the camera? This is very useful. I'm very thankful that somebody did it.
If you have to do it.
Exactly.
Okay. And you will show more on Wednesday in the tutorials also, and.
Will I? Okay. Okay.
I know something.
Okay.
Let's see more time stepping also next time.
I will try to have time stepping implemented by then. Yeah. So maybe this is so now NGSolve has time steppers, and we have you can use PETSc TS, which is the PETSc time stepper. I have no clue where this is. Yeah. So you do time. You can solve. You have all these different time stepper implemented that you can play with.